Yes, so I'd like to welcome you to our first technical malfunction that we have now so swiftly dealt with, which only shows the professionalism of our team. So without further ado, I'd like to introduce our first speaker, Brandon Rhodes. Now, Brandon is happy to be back in Poland for his 6th conference here. Normally, Brandon lives in Indiana, where he has a 128-year-old house, and the house needs so many repairs that it's a project in itself. And Brandon set up an Instagram account to his house, and it is so popular that it now has over 300 followers. Now, classic design patterns, where are they now? Let's have a round of applause for Brandon Rhodes.
Thank you very much. I am delighted to be back in Poland. I am delighted that Code Dive is back in person. And yes, as just announced, I am here to talk to you about the classic design patterns. Where are they now? Design Patterns was a book that came out back in the 90s. It was a long time ago, but I still see questions about it online, and so I thought it would be interesting to review whether any of the book is still relevant today. It came out in '94. It was a book on a fad at the time called object-oriented programming. It was by 4 people that no one could remember the names of, so they just called them the Gang of 4 because there weren't any other programming books written by 4 people. It described 23 design patterns, they called them, that had become common solutions for the problems with these newfangled object-oriented languages. My goal for this talk is to make a brief survey of the 23 patterns, asking these questions. Can we learn anything from the ones that survived? Can we learn anything from the ones that did not? There will be limitations to this talk. I'm going to have to cover 23 design patterns in under an hour. There will not, therefore, be much time for nuance or corner cases. It reflects my experience programming, a lot of Python, less C and C++, not your experiences, which might be different. And it will not be entirely fair towards the visitor pattern, for which I apologize in advance. But that's OK. It's fine if your list of relevant patterns is different than mine by the time we finish the talk. The goal is for these old patterns to help us reflect on how we program today. Happily, the Design Patterns book is online, so you can review the patterns yourself later to develop your own opinions if you don't like mine. If you look up Design Patterns Gang of 4, this unc.edu site from a CS professor should be high in the results and has the full text of the original copy of the book, with all the code examples, mostly in Smalltalk and C++. Some of my own ideas on design patterns as they apply to Python are online if you want to check those afterwards as well. So, are you ready? Here we go. 23 patterns that they grouped into 3. And what should we go with first? The ones that maybe survived or the ones that did not? First, let's cross off the patterns that didn't really wind up being relevant if your programming language offers first-class functions. What are first-class functions, I hear you cry? Those are functions that can be passed as an argument to another procedure or routine and placed in a data structure and associated with data. You might think, what language doesn't allow that? Smalltalk was the language available in '94. The pioneer language of object orientation didn't let you pass functions or procedures. So there were a number of design patterns that were just kind of trying to get around this problem with Smalltalk and some of its descendant languages. Let's look at them quickly. The factory method said, all right, well, what if we need to give a piece of code to a big class-like application? Big classes like that were popular back then because just to bring up a window on the screen could take 100 lines of code in '94. In Windows or on a Mac, you want to wrap that up in an object. So the idea was, oh, well, if Once the application object is up and running, if it needs to know how to create your document, it doesn't know whether you're programming a spreadsheet or a word processor, it's going to need to know how to call a create document procedure that builds and returns an instance of your document class. Well, how could it do that if we can't pass functions? So their idea was that you would subclass application. Yes, make your entire own subclass of application just to add one line of code. Not only does that sound hopelessly awkward today, but even design patterns itself, back in 1994, offered a better approach. 2 chapters earlier, they had already described the abstract factory. The abstract factory says, let's not make a subclass of application. Let's instead design application so that it takes as a constructor argument a little bitty class that has your special line of code in it that knows how to build your particular subclass of document. Why should we prefer that second pattern, the abstract factory, over the first one, the factory method? Because of a fundamental design principle from the introduction chapter of the design patterns book itself. In fact, it was so important that they didn't bury it in a paragraph. They put it on a line by itself, just like this, in italics, just like this. Favor object composition over class inheritance. One of the fundamental principles of the book. What is composition? You have, in their terms, composed 2 objects when you give one of them a reference to the other. So if I create F, a my document factory, and then pass it as a constructor argument to the application that it saves as an instance variable, I have composed those 2 objects. Favor object composition over class inheritance. Why? Go read the introduction to read the full slate of reasons, but a quick one I'll mention is because putting objects together dynamically at runtime is simply more flexible than writing a bunch of extra classes at compile time. And so they always favor object composition. Factory method, well, it's class inheritance. The abstract factory, as we saw a minute ago, does the same thing with object composition, and so it is the better pattern, by their own rules. So you might ask, well, then why did design patterns include the factory method? Why write an entire chapter on it if a better alternative already existed? And this is something important to understand. Because they wanted the book to be a complete catalog of all common object-oriented practices. They did not limit themselves to best practices. They wanted you to be able to find all the patterns you were likely to encounter in 1994 programming. And the factory method, despite its awkwardness, was in widespread use. In their own words, factory methods pervade toolkits and frameworks, and they were able offhand to give a long list of frameworks that were always having you subclass in order to specialize. So, they had 2 different ways to parameterize object creation. But neither one is a pattern that we tend to use in modern languages. I go years at a time without seeing either of those patterns. Because our languages today have first-class functions. And in that case, you don't need to pass application an instance of a class that you've attached a method to. You just pass in your constructor function. Some languages even have first-class types, and you can just pass the class itself to be instantiated. And so, those 2 patterns have largely fallen out of use among people that use modern, especially dynamic, languages. All right, what about some of these other patterns? Let's go ahead down in the lower right and look at template method. Template method should look familiar. It should look like the one of the 2 patterns we just looked at. This asks, what if application needs you to give it 3 procedures, not 1? Well, then you should have to write a subclass and override the 3 abstract methods with 3 concrete procedures. By the logic of the book's own introduction that we should favor object composition over class inheritance, I think it's clear that rather than getting a huge object that you don't understand the internals of and trying to write 3 new methods for it, it would be much clearer if you just had a separate type that you subclassed and built off of to provide the 3 methods that this fictional application needs you as the programmer to provide to it. So by the book's own logic, let's also go ahead and cross off template method. All right, up to the left, prototype pattern. That was actually kind of interesting. Imagine, they say in their chapter, that we're writing a music composition application that wants to let users create 4 kinds of object. Here they are. Notice, and this is the challenge, they're of different classes, different subclasses of some parent class, rest and note. And some of their constructors need arguments and some don't. So it's kind of a mixed bag, the rules by which you create these. Now, how could you explain to, say, a menu widget that's going to be on the screen, how to create these objects when menu items are selected, when some of them have different classes and some of them have different constructor arguments? Now, in a modern language, of course, you're already thinking, you could just pass a data structure. The people who designed the menu system probably just want a plain data structure with the names of some menu items, the callable, the function, the type that needs to be invoked, and then any arguments that they need. All right, but the Gang of Four, 1994, have to ask, what if your language isn't that powerful? Are you going to need as many factories as kinds of objects that you want to create? Not just one per class, but even one per individual kind of note? The prototype pattern said, no. Simply create examples of the 4 objects and give them each a clone method. The idea here is that if you give a collection of objects a clone method, where what happens when you call clone, well, it builds and returns to you a new instance using the same constructor arguments as were used to construct the object you're calling, then if I have 3 kinds of note, I just instantiate them, I pass them to the framework, and it calls clone to get new copies of notes with the same constructor argument. You've replaced needing to have a whole slate of separate constructors with just needing a clone method on each class. Thanks to the prototype pattern's clone method, we can give plain object instances to the menu instead of separate factories. It's an interesting solution to a problem. I don't actually dislike it. I've just never seen it before. I have never seen that problem come up in modern languages because we just don't get into that situation. Though I have to admit, I like the solution and find it elegant at a level that I don't for these first few patterns that we crossed off. All right, the next one's the singleton. I'm not going to spend much time on this. Singletons are those annoying global objects that code seems to need access to, but you don't want to pass everywhere. Do we need singletons? Sometimes, maybe. That's a big topic of its own, and people give entire talks about singletons. But do we need the singleton pattern? If you go look at their chapter, they have this whole elaborate story about how you contort the class itself to force it to be used as a singleton. It refuses to build multiple copies of the class so that it can only be used as a singleton. Do we need that pattern, even if we need singletons? In my experience, no. And in fact, I've been in million-line code bases before in some of my work and never seen the singleton pattern. Just write the class normally, build a single instance, and provide a global name or a global function that returns that instance. From the Python standard library, you call logging.getLogger, and everyone who calls that gets the same object back, so you're all logging to the same file. It works fine without the pattern. Why avoid the singleton pattern? Again, it's a whole technical discussion of its own, but one hint of why is, reason that's easy to explain, is that testing becomes hard and tests of the singleton become coupled if you really truly can't create a fresh instance so that all of your tests are having to share. That's just one reason not to follow their contorted pattern for delivering singletons. And so, I don't encounter it in practice, and so we cross it out. We're making progress. All right, one last one that tends to disappear because of the power of modern languages is the strategy pattern. The strategy pattern, all right, their example is, well, what if you had an object that needed to be given a specific paragraph-breaking routine at runtime out of 3 that are available? At runtime, right, so you can't specify it when it compiles, because it might be a config file or something that selects it. Strategy pattern says, well, put the 3 versions of the routine in 3 single method classes, build an instance of each, and pass them as constructor arguments at runtime to the routine that needs them. This is their diagram from the book. By the way, all of the diagrams I'm using are theirs from the book, the official ones, showing how if you need a compositor that can split paragraphs into lines on a page, you might write 3 specific subclasses of the compositor and then can build an instance and pass it to the composition object at runtime when it is ready to call compositor compose. We today can solve this more simply. In any modern language, you solve this problem by just writing 3 functions and passing one in as an argument. Done. Once again, we don't have to wrap up a procedure as a method of a class of which we build an instance. We just pass procedures around when we need them. So, in my experience, the strategy pattern never comes up in modern languages, and so, for my purposes, I cross it off. All right, in powerful modern languages, these 6 patterns disappear because they aren't needed. So we're down to 17, making some progress. What should we tackle next? Well, since we're on the topic of programming languages, there are 2 patterns that are also disappearing from our code, but it's because they're so useful. They're now getting built into our languages. These are the iterator and the visitor pattern. I'll describe them briefly. Both of them involve a producer object, which is going to build or retrieve items, and a consumer object that wants to iterate over those items without needing to know the details of how they're being produced or stored. The 2 patterns are opposites of each other. The iterator pattern says, well, let's write the producer to offer a callback method. Very often it has a name like next. The consumer then loops, calling next over and over until the producer is done delivering objects. Visitor pattern is the opposite. The producer is in control, iterating across a tree or other data structure, and calling the consumer, which offers 1 or more callback methods that are used to deliver the next item. In legacy languages, you have to choose one approach or the other. Either way, someone's class has to suffer from callback-style programming. The solution to this, which was actually invented in the 70s, is called generators. They were in a pair of obscure languages and were revived. The pattern generators were revived in 2001 when Python added them. They were so popular they've now been added to C#, JavaScript, and Ruby. What is this idea, and why is it taking the world by storm? Well, before generators, you had to write up the iterator pattern yourself. You had to make a little class with a next method. This is just, it counts from 1 to 10. And you had to have a convention for building objects and then signaling when you were done delivering them. And you had to write it yourself. After generators have been added to your language, you get a new keyword, control flow keyword called yield. You now just write a normal loop and yield each time you have a new item that's ready for delivery to the consumer. Each time the consumer asks for an item, the producer runs enough code to reach its next yield and deliver the item. So the consumer's requests for more items gradually cause the producer, one step at a time, to run all the way to completion. So both the producer and consumer can be written with normal control flow statements like if and for and while, things we're all familiar with. Neither is forced to define methods or endure callbacks. Here, they can both just use a simple for loop. Passing a producer to a consumer works exactly as though you had implemented the iterator pattern by hand and written a class with a next method that returns a lot of objects. Except, I'm going to go on a tangent for one moment, if you will allow me. Don't actually let a consumer talk to a producer. Here, I just want to touch briefly on an important aspect in application design as opposed to object design. They're different things. If you have the consumer drive the producer directly by passing it in and letting the consumer cause the producer's code to be run, well, your main thread loses control. All of the action happens in that last line of code, with the main thread being out of the loop, literally. I call this domino programming, and it really, really dominated object orientation, especially back in the 90s. I don't mean the game dominoes. I mean, as a kid, did you ever set up a line of dominoes standing up on end, trying to get it where when you pressed the first one, everything else would fall over, but you were out of control once it started happening? Domino programming is where instead of just doing in your main thread of control a series of actions, you instead are setting up a bunch of classes that all know about each other so that when you tip over the first domino, everything out of your control, everything that's supposed to happen does. This is domino programming, and I believe in many cases it's an anti-pattern for your main thread of control to surrender to other classes the question of what happens next. Here's an idea. Instead, run the producer to completion and save the output in a plain, flat data structure, maybe a list. Get the producer done, then pass the list to the consumer, a flat data structure. This idea may sound silly when we're only talking about one producer and one consumer, but as an application grows, you should always prefer shallow call stacks to deep ones. It's a good day when you can draw a bright line across your code and say, everything above this line has finished running, and the only thing crossing this line is a simple, inert data structure. Here's where we can draw the line if we're the one that runs the producer to completion. Now, yes, sometimes you want them to talk together, right? Because if it's a video streaming service, you want to go ahead and be getting data on the wire. You want the main loop to stand aside and let data start flowing. But if you're not in a situation where you're going to run out of RAM from the size of the list and you don't need live streaming, think about making sections of code independent of each other where it's only a data structure that passes from one piece of your main routine to the next, where you're able to draw that bright line where execution of everything above it has finished, the objects have gone inert or been deallocated, and plain data that you can look at and debug is the thing passing to the next phase of your program. Why? There are a number of reasons, and it would be a talk of its own for me to go into all of them. But at the core of what I'm trying to say is this, that data is easier to reason about than control flow. An old book from 1975 on why software projects are always delivered late was called The Mythical Man Month by Fred Brooks, and he said, show me your flow chart, the diagram that shows how control flow will pass in your code, and conceal your tables, and I shall continue to be mystified. But show me your tables, your data structures, and I won't usually need your flow chart. It'll be obvious. He found, as I do, data, easy to read about. Code and control flow, more difficult. So that's one reason to prefer keeping control and using data to link parts of your program rather than verbs and actions. Love your data. Heart your data in Unicode. Be jealous of getting to see your data and not just having it pass anonymously between routines. Things are easier to control and debug and expand later if your main routine is in control of as much data as it can. All right, end of tangent. Iterator and visitor, great patterns, but I don't write next methods anymore because the languages I use have now built both of those patterns into the language, so they're still there. They're powerful and they're working. But as design patterns, they disappear from my code because I no longer have to implement them. So for the purposes of this talk, of what I actually write as classes these days, I'm crossing them off the list. All right, only 15 left. Are there any more that we can eliminate? I think there are 3. Proxy, memento, and observer. What are these? Proxy actually has several branches, several uses, but I will limit myself so the talk doesn't go long to the remote proxy, which was the most famous and widespread use of the pattern, where the methods of a class send requests across the network. It looks like you have a user class right in memory, but in fact, every method call is actually going to another server to get the return value. Second, the memento. Memento is an object state saved as a binary string. So right, your big application is about to exit, but you want to be able to rebuild its state when it comes back up. The memento pattern says, well, teach the object to write itself out as bytes, and then when you run the application again, you can read the bytes back in, and the object will be recreated. The observer pattern, finally, is where an object can offer subscriptions to its changes, and other objects, called subscribers, can receive callbacks when the data in the object changes. So why am I putting these three patterns together? I will explain it by explaining what are their sins. What did they each do wrong? The proxy pattern hides how data's passed across the network. Somehow, the method calls are getting passed across the network, but you don't know how. The memento pattern hides how data is persisted to disk. It's just a binary blob that you don't know how to introspect. And the observer pattern scatters data across a bunch of objects that communicate now about changes, rather than unifying it. In other words, all three patterns do something wrong with data. And you should love your data. You want to see it. You want to be in control of it. You don't want it to disappear and be in an obscure private format that you don't understand. So in the jobs I've had over the last 10 or 15 years, the code bases large and small I've worked on, I don't see the proxy pattern. In the projects I've been on, network APIs between services should use a data format you understand and can document. There's many good options today. And be handcrafted to make sense over a high latency channel. Good object methods for things that are in memory tend to be small, orthogonal, and numerous. Good remote procedures tend to be comprehensive, aggregate, and few. And as an example, a class might offer getters and setters for all of its 11 instance variables separately, but a network call would probably want to return all 11 at once and set as many as you want to provide when you do a write. Whole different set of design decisions when you're going remote over doing method calls to things in RAM. Second, the memento pattern. Data should be persisted in a format that's independent of your programming language and that you can access directly using other tools. And there's a lot of good options today, open source, even like they weren't in '94, for storing information so that you can get to it later, and so that if you're having to debug something at 3 in the morning, there are other tools besides maybe the broken code that was pushed late at night for getting into that data and finding out what's going on. Finally, the observer pattern, should we really be building forests of objects that are subscribed to each other's state changes? Turns out the answer is no. I don't have time to tell the long, sad story, but go look on YouTube for any recent Facebook talk about their React library and about how hard it was to make the Facebook page you see on the web stay consistent if there were a single piece of data that, say, a notification, that could be several places on the screen at once. React today is the most popular JS library as of a few months ago. It's actually knocked jQuery, which felt like would be there forever, off of the throne and is now being used in more current projects than any other JavaScript library. Why is it so popular? What is the secret to React's success? Data. It says that instead of your data being living on a bunch of live objects that are trying to send each other updates, your data should be simple, it should be inert, Essentially, you get all of the data that the application page knows about. Say you're at facebook.com. Everything you're seeing, all the information you're seeing is sitting in a plain JSON data hierarchical object. Clicks, keystrokes, and server events are not allowed to go touch views and objects on the screen. They have to write to that inert data structure, updating its hierarchy and overriding things. Then React actually diffs the object, or what the views should be with what they were previously, and goes and updates the screen for you. So a simple, well, perhaps a very large data structure, but a hierarchical inert data structure that it's easy to view and reason about is the only place where events can coordinate with views, and it's become the most popular JavaScript library because it's so much easier than having objects trying to update each other by putting data in the center. So React makes a single data structure the foundation of your application. The proxy, the memento, and the observer, all three of these patterns fail to put data first, and you should heart your data. And that, I think, is why in the last decade of programming, I cannot remember seeing a single one of those patterns once. So we get to cross 3 more of them off. All right, we've essentially eliminated half. We've knocked out 11 of them, leaving a dozen left. And at this point, I think I can't go farther. At this point, I think that I've run out of patterns that I can easily knock down as being irrelevant or anti-patterns. So let's get the ones that have survived, and let's look at them in groups and see how they work. First, we will look at these 4, because they all have something in common: bridge, decorator, mediator, and state. They are each fairly complicated, and alas, I can only summarize them very quickly. The bridge is the idea that one real-world object, like a window on the screen on your computer, might be implemented best by 2 classes. Some of the people writing the very first application frameworks found that you want to specialize the window according to whether it's a little pop-up window or whether it's showing icons, because that affects its layout and behavior. But you also need to subclass window because we have more than one operating system we want to support, and the low-level windowing routines on each OS are quite different. And that requires you to subclass in 2 directions at once and then have a large number of subclasses unless you split the window into 2. So they had this idea. When your application code asks for a window, it actually builds 2 objects. The window object that you see is the high-level one that knows how it should behave and how its data should be laid out. But secretly, it creates a low-level window imp object behind it that knows how to talk to the operating system. 1 real-world object, but 2 classes. That was the bridge pattern. All right, second, decorator. The idea here was to write a wrapper class with the same interface as the object wrapped. They were thinking, what if you have a text view? Class that knows how to draw text on a bitmap. What if you now want to add scroll bars to it, but you don't want to make it more complicated? Well, they thought, what if you write, so a text view has a draw method, knows how to draw text. What if you made a scroll decorator? A class that when it's asked to draw, turns around and asks the text view to draw, gets the resulting bitmap, cuts out a portion of it that will fit on the screen, and draws a pair of little scroll bars around it. Now you can have scroll bars, and the text view doesn't even know they're there. It doesn't know that only part of it is showing on the screen. And once you've come up with that idea, that the scroll decorator accepts the same interface, or offers the same interface as it uses for the view behind it, you realize that you can stack these endlessly. You could have them do logging. You could have them on some kinds of objects do different kinds of protection. You can stack decorators as deep as you want because they offer the same interface they accept. So a decorator is a valid thing to wrap with another decorator of the same interface. All right, that's that pattern. Third, the mediator. Now, here we have a list box and an entry field. And I know what you're going to tell me, Brandon, you just told me to use React. But this imagines it's just a very simple interface, a list box and an entry field, so we'll go with it. And the idea here is, sometimes in a dialog box, if you edit one thing, the options available on the other one change. And this pattern simply says that you shouldn't put that code in either the list box or the entry field. In other words, you shouldn't do a pair of observers watching for changes in each other. How about you split that out into a separate procedure, lower left here, widget changed, that when either of them is edited, calls a single procedure that then tries to get everything straight again. Instead of a bunch of objects that talk to each other, have another layer on top. That's the idea of a mediator. Finally, and this one was a little interesting. I'd never seen it before. They had one called state. What happened is they implemented a TCP connection using object orientation, and they noted that every single method had to start with the same if statement. If the connection is open, do one thing, otherwise return nothing or raise an error. Next method, check if it's open. If it is, do one thing. If the connection's closed, return nothing or raise an error. And they noticed that every single method had to have, is it open already? Well, they reasoned that maybe we could get rid of all those if statements if we had some secret objects in the background where we could define the stack of what the methods do if it's open, and then a separate object that had the stack of methods that get called if it's closed. That idea that the TCP connection you're using as one object might swap out a back-end object depending on its state is called the state pattern. It replaces if-else stacks with what are simply separate objects. Bridge, decorator, mediator, state. What do they have in common? Why did I put them together? They all break the old object-oriented assumption that one real-world object should become one object in your code. Some of the people who invented Smalltalk and were using it in the late 80s, early 90s, thought that this would be the solution to how we organize code, because code, right, it always gets tangled. And they thought that if they made the rule that if everything that can happen to a window is on a single window object, if everything that can happen to the database row is in a single object, our code wouldn't be tangled anymore. Turns out that's not true, and all four of these patterns are breaking that assumption and are starting to say, you know, maybe it makes sense to split behaviors out into several classes, even for what is conceptually a single window on the screen. All of these classes, three of them are essentially kind of pulling behaviors off and layering it on top of what might have been a single object. And then the state is getting behaviors and secretly behind the class you're using, pulling behaviors out. But you can see that all of these classes are breaking apart the old object-oriented pattern of every single thing that can happen to an object living as a method on it. These four patterns essentially all begin a disassembly of object orientation, right in the middle of the most famous book on that subject, and start using classes to organize procedures into layers rather than to represent data. In the same way that as we went through our first patterns, we were talking about getting data out and giving it a life separately from objects, these patterns are getting actions, getting behaviors and pulling them out and giving them a separate life as well. And that's an interesting enough move in the world of object orientation, especially in the 90s, that I'm going to keep them, even though I honestly have rarely used these four patterns. I think they're keepers because if I did wind up in one of those exact situations, I think I would be likely to use them. I know what you're about to say. Brandon, isn't that domino programming? Isn't this setting up classes so that you call one thing and then automatically another thing and another thing gets called? To which I have to say that's an interesting point. And I think you're right. And it is indeed, to some extent, domino programming. Knock over the first decorator and calls start happening automatically. But They are elegant enough and constrained enough that I think I could live with them. I think I would still understand what my code was doing. So for the purpose of this talk, they're staying. All right. Next, we'll just look at 3 small sort of standalone patterns that are all in widespread use today. The builder pattern says, provide a single object whose API builds and returns an object hierarchy for us, right? Why make you, if a bunch of objects need to exist, worry about how they need to be instantiated and connected together if someone else can do it for you? Example, the matplotlib library for drawing diagrams under Python, it has an axis object. That has, down in the lower left here, you can say, axis, plot this data. Axis, annotate, and put some annotations on the chart. And you don't have to worry about what plot objects look like, or annotation objects, or what references they need to each other if they're going to render successfully when the time comes. The axis object handles that for you. Builder pattern, when it works and when it fits an API, is really, really great because your code neither has to worry about nor become coupled with how back-end representations are being built. Second, the adapter pattern. When a class doesn't offer the interface you need, write a wrapper class that does and have its methods call the underlying object. A Python standard library. Sockets have a .makefile method that returns an adapter that looks like a file object, but whose read and write methods really call the sockets receive and send methods. So if someone on your team has written code that thought it would be writing to a file, can pass it this object, and now the data will go across the network without needing to edit your friend's code. That's the adapter pattern. The flyweight pattern, finally, says that small read-only data can be shared between object instances. This came up a lot when they were writing the very first versions of presentation libraries. They noticed that if you put the letter A on the screen in 2 places, that the x and y coordinates will be different, but that the dimensions of the letter are the same, yet you're copying that information into all of these different glyphs. Why not have a read-only, so that it can be safely shared, little data object that keeps the information that's constant and shared between all instances of the letter A, and pull off into the glyph only the x and y that differ between them? Pulling off read-only data like this is called, again, the flyweight pattern. As an example, the integers, -5 through 256 in Python are flyweight objects, right? Python, everything is an object. Well, that's going to be so inefficient. You're going to have to build integers all the time. Well, they actually avoid some of that expense by going ahead and pre-building sort of the most popular integers so that each time a calculation in Python returns an integer in that range, like 17 or something, it's the same object that gets returned every time. That, again, is called a flyweight. So I encounter all 3 of these patterns fairly frequently. They, from 1994, wound up being keepers. All right, are you ready? Now we're going to look at the really big patterns, the ones that have wound up governing the way our main applications operate today. The composite, the chain of responsibility, the command, and the interpreter. What are these? Well, the composite pattern, by the way, I call these the framework patterns because they're not ones that I tend to sit down and write. They're ones that I tend to sit down and use. Composite says, give all nodes in a hierarchy the same interface. Instead of giving the middle nodes one interface and the leaf nodes another. The idea here is that if you're doing a hierarchy of items in a drawing, lines and rectangles and things like that, go ahead and make the aggregate object, the picture, an instance of graphic as well. That way, pictures can hold other pictures, and your hierarchy has all the way down to the bottom, has a consistent interface. I know many of you instantly are thinking of the DOM, the document object model that underlies all web programming, because it uses the composite pattern. A div can hold things inside of it. An image cannot. And yet they both have the same object interface in the DOM. Not only do they both have a tag name, which of course they both have, But even image has a .children list, even though it is always empty, because it makes programming simple. You can run across all of the objects in the DOM asking about their .children, and you don't have to have an if statement and remember the rule that images can't have any. They offer the exact same interface all the way down to the bottom. Makes programming simple. It's called the composite pattern. Next, the chain of responsibility. In a composite UI hierarchy in the browser or elsewhere, there was this pattern in 1994 where you pass unprocessed clicks and keystrokes up to your parent. This is universal and is called bubbling in the browser. So you click on the piece of text, and it's like, I don't care. I don't want to be clicked on. But it gets passed up to the button that the text is inside of, and the button now knows it's been pressed. Again, that is universal, and it is used everywhere. The command pattern, said to represent user actions as a list of objects that have both do and undo methods, because it's so tempting when you're first programming and the user hits the letter A to just add the letter A to the buffer. Command pattern says, no, no, no. Instantiate a typed A object and call its do method to add A to that text field, so that when the user then hits Control-Z undo, you can run the undo method on the action and step backwards. This is universal in browsers and GUI frameworks today. It turns out that the command pattern is also useful in other contexts. I don't use Django, a very popular web framework, but I saw a talk on it a couple of years ago about their new migration system. Django lets you define what your database tables should look like using a declarative syntax. And as your application evolves, your models change. As your models change, Django saves those database migrations using the command pattern so that you can both apply each migration in production to move forward, but also undo a migration to recover and move back. So it remembers the modifications you've made over your application lifetime. You can undo them later because of the command pattern. Finally, the interpreter. It uses the composite pattern to represent an abstract syntax tree and make it executable by giving each node a method. What do I mean? If you want, in a spreadsheet or something else, a user to be able to type n+1, you parse n+1 and traditionally build an abstract syntax tree that says, oh, we have an add operation with 2 arguments. In many places, the next step would be to then compile that to bytecode or machine code, but that requires a lot of extra machinery. This pattern says, just give them an eval method. Don't bother compiling. Don't bother inventing or adopting a bytecode. Just give each node in your abstract syntax tree an eval method that goes ahead and grabs the value of n or returns the value 1, and then the add method can add those together and return the result. So abstract syntax trees become executable, and you can let users type expressions on the fly, or you can let expressions live in config files without having a compiler around. And so those 4 patterns have become absolutely huge and have really moved to the center of how user interfaces are implemented today. I don't implement browsers, so I don't sit down and write them, but I am constantly a user of those patterns, as in some form are we all. Oh, there's one left, and it winds up in an odd little position, and we'll finish with it. Facade says, hide a complex system when you can behind a single API class. That way, as objects come and go, the caller doesn't need to know. They just call methods on the facade. Problem, it actually doesn't wind up working in practice. To qualify as a facade pattern, an API, per the way they wrote the chapter, must live on only one object. But real-world APIs almost always use several. Here's 2 quick examples in jQuery. Well, it has this single $sign that you keep calling to do searches for elements. Is that a facade? No, because the rest of the API is the query objects that you get back with the list of the elements you selected, and every query results in a different object. So it's a little collection of objects that jQuery is using to let you talk about the DOM. One of the most popular libraries today is the Pandas data frame object, where you can read CSV, all right, their second line. You can, with a single line of code, read in a big data file. And it almost at first looks like a facade. You can ask the size and the columns on that one object. But it's not a facade, because once you start wanting to go do math using the individual columns of the CSV file, like name and amount, it's returning smaller series objects, which are a second layer of object you're talking to. So it's not, strictly speaking, a facade. Facade has to be one object, and our really, really real-world popular APIs today are typically several objects. Also, the design patterns example of a facade, they don't set this as a rule, but it provides no access to the underlying subsystem. But real-world APIs are usually happy to let you access the lower level. You can ask jQuery for the underlying DOM element. You can ask NumPy for pandas for the underlying array. They're not trying to hide the details. They're just trying to make them convenient, but want to let you drill down when you need to. So that facade winds up in kind of a twilight zone where it sounded like a great idea. It just rarely works out. So we've made it. We've completed our survey. 6 patterns, useless if you have first-class functions. 2 have become language built-ins. And 3 are real anti-patterns that obscure our data. But half of them, I would say, survived. 4 were rare but useful for decomposing big classes. 3, small but useful. 4 are huge and dominate our frameworks. And finally, 1 final pattern was ambitious, but fatally limited. That's my tally. You might have your own. Thank you very much for your attention during this whirlwind tour. I'm Brandon Rhodes. Thank you very much.